Yeah, I'm really honored to be here. I'm happy to see lots of students. I teach astronomy to about 100, this many students, so this feels great. And today, I just want to share this awesome project that I'm really passionate about that I've shared with my students. And it's about mapping the Milky Way. So the Milky Way is a spiral galaxy, right? Raise your hand if you know that. Raise your hand if you know this. Okay, how do you know? Probably you heard it somewhere, right? Have you done the data analysis? That's what we're going to do today. We're going to do some awesome Milky Way data analysis. So like my awesome introductor said, we can't leave the Milky Way. We're stuck inside of it. It is our galaxy, and our galaxy is too big to just casually leave. So imagine you're like this sad puppy dog right here, and you have to figure out what your house looks like, but you can't go outside. And so you look out the window and you look at other houses and you dream of maybe one of those being like yours. Maybe you live in a huge mansion. Maybe you have bricks on the outside of your house. Or maybe you live in a small shack and you have wood making up your house. So we're like this sad puppy dog right now. We can't get out of our galaxy. We just have to look out the window. And this is what it looks like. Raise your hand if you've seen the Milky Way in the night sky. Awesome. There's some good dark skies in Nebraska. Awesome. Yeah, so this is the Milky Way stretching across the sky, and that's our view of what it looks like outside of the window. So the best we can do is look at other galaxies and say, hey, maybe we look like one of them. So here's some pictures of other galaxies we can see, and some of them are blob-like, orangish. Some of them have more blue colors and spiral shapes. Some of them are more flat. So maybe we look like one of them. And in fact, maybe if you had to choose between a blob and a disk, based on what you see in the night sky, what would you choose? Probably a disk, right? So let's start with that assumption. We're going to assume that the Milky Way is a frisbee-like disk. We see other galaxies that look like that, and so we're going to start with that assumption. It's a pretty reasonable assumption, right? Okay. So fortunately, we can see a bunch of star clusters that look like this, that kind of stretch they kind of surround the Milky Way in a sort of spherical shape. They're just evenly distributed. So fortunately, we can kind of see most of those and map out the distribution of where they are. And we can see that we're not at the middle of the spherical distribution. We're sort of on the outskirts. So the sun, if this is a top-down view of the disk that we're imagining the Milky Way to be, the sun is about 26,000 light years from the center of this distribution. And the distribution as a whole is about 100,000 light years across. That's really big, right? It would take 100,000 years traveling at the speed of light to go from one edge of the galaxy to the other, underscoring the fact that we really can't do it. So, okay, we have this hypothesis, we have this model that we're ready to use. Let's try to study what we actually see. Oh, what we actually see is a lot of clouds and dust. So that's not that good, right? It's hard to see the galaxy when there's like a cloud blocking your view. So unfortunately, the kind of light that our eyes see isn't a good way to study the galaxy. So we would get wrong information. We would miss out on a lot of what's out there. Fortunately, radio waves, with their long wavelength, can just travel right on through that dust and gas. And they're fine going through the galaxy. So here's a picture or a map of the galaxy with radio waves. And we can see, I don't see anything obstructing our view. So radio waves are a really good way to study the Milky Way. They can go right through those clouds of gas and dust. So we need a radio observatory. How can I access one of those? That's pretty hard to come by. But fortunately, we can control a radio telescope online. So the Green Bank Observatory, which is in Pocahontas County, West Virginia, is one of the premier observatories for radio astronomy in the whole world. They've got many, many radio telescopes, and they look like satellite dishes, right? But it's a telescope. And that radio telescope is called the 20-meter telescope. It's 20 meters in diameter, so it's pretty big. And like I said, you can control it online with Skynet. Anyone watch The Terminator? Yeah, it's not a different Skynet, okay? First of all, it's not just any old radio wave, it's a very special radio wave. It comes from this transition. It's called a spin flip transition. So raise your hand if you've heard of hydrogen before. What is hydrogen made of? A proton and an electron, and that's it, right? So that quantum mechanical property of spin means that they can be aligned or anti-aligned. And one of those is higher energy than the other one. And so what do you think it wants to do? It wants to relax. And when it relaxes, that energy's got to go somewhere. It creates a radio wave. And the length of that radio wave, the wavelength, is 21 centimeters. So hold your hands up. How big is 21 centimeters? No. Yeah, closer to that, right? 21 centimeters. So this 21 centimeter wavelength radio waves are streaming down to us constantly from the Milky Way. All we need is a cool telescope to catch them. And if you think about it in frequency, that's 1,420.41 megahertz. What's a megahertz? How many hertz is mega? Mega is not giga. Is it a million or a billion or a trillion? Million megahertz. So 1,420.41 million waves every second are hitting the telescope. That's what a megahertz is. Million waves every second. So we've probably, raise your hand if you've listened to the radio. Yeah, so what's your favorite radio station? 89.7? 89.7 what? What are the units? Megahertz. So this signal from the Milky Way, is it a higher frequency or a lower frequency than your radio station? Higher, right. But really no different. If you could only turn your radio knob up even higher, 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 maybe you could catch this signal from the Milky Way too. So that's what we're doing. We're kind of tune into this signal, this particular signal from the Milky Way, because hydrogen is everywhere. Hydrogen is the most abundant element in the whole universe. So this is going to give us a great map of the Milky Way. Thumbs up? Awesome. So you each have a different piece of data from a different part of the galaxy. So each of those dots represents a different location where my students collected data. You actually have students, or data that my students collected. I actually didn't take it myself. And everybody has a galactic latitude of 0. Remember that disk shape? 0 latitude means we're not looking above the disk or below the disk, right? So everyone has a latitude of 0. We want to look in the disk. But everyone has a different longitude, right? So if I'm in the disk, everyone has a different longitude of where we're trying to look. And it's printed on your sheet there. So now you know where you're looking, sort of. I haven't told you the complete picture, because we need to define our coordinate system. We're pretty self-centered, so we put it here. The center of the coordinate system is in our solar system. It's the sun. And we basically just define, when we look through the galactic center, that's a galactic longitude of 0. Raise your hand if you have a galactic longitude of less than 25. Raise your hand. Probably not many. Okay. Okay, maybe we didn't get an even distribution of the data. There's more. Maybe people can have twice the data. So then when you look at 90 degrees, we just define that as that direction. That's just how we defined it. 180 degrees, that makes sense. You're looking straight away from the center of the galaxy towards the outskirts of the galaxy. And it loops back to full circle, which is how many degrees? 360. Okay, so now you can kind of orient. Give me a thumbs up when you've oriented where your galactic longitude is, where you have an idea of where you are looking. Okay, let's keep going. So your data looks like this, right? I've kind of zoomed in, so yours is probably more stretched out than that. And I want you to I want you to do data analysis here and try to estimate which frequency the different peaks of your data are at. And the x-axis is the frequency. I cut off the y-axis because we don't really care about it right now. So if you can scan, or maybe you can share and help each other out, we've got a Google form going, so I'll give you a couple minutes to figure that out. So go. So here's the, oh my gosh, you guys, look at this. This is all of your data, just submitted today. They're coming in right now, coming in live. Got a 6 right there. This is good. This happens all the time. This is great. Look at them. They're all near that special frequency. Does anyone remember the special radio station of the Milky Way? Shout it out. 1,420.41 megahertz. Yep. I tell my students to sleep, like dream that. Just memorize it so much that you're just shouting it out on the streets. 1420.41 megahertz. 1420.41 megahertz. Okay. So we've got a lot of data, and wow, it's beautiful. What does it mean? So let's actually start to think collectively. Whoops. So when we work together, we get a big, big list of data. All of your data, when I just looked at it, was in order of when you turned it in, right? Is that the best way to analyze the universe? No. So if you were going to arrange this data in a useful format to study the Milky Way, what would you put it in order of? Degrees longitude, yeah. I realize you can't read it. That's the point. It's okay. Yeah, so this is a screenshot of all the data that my students took. This is their data, but then their analysis of it, which hopefully is very similar to your analysis because you're looking at the same data. And this is arranged in order of galactic longitude. And when we work together, we get a very broad sample of the entire Milky Way. Does anyone have a galactic longitude less than 3 degrees? Didn't think so. I didn't make any. Does anyone have a galactic longitude greater than 238? Same thing. I didn't make any. So the reason is you need to go to the southern hemisphere to see the rest. The entire Milky Way isn't visible from West Virginia. So we don't have that data, but maybe we can still say something useful about the Milky Way. So this is all your data. And do you think it's a little bit weird that we didn't get the special frequency of 1420.41 megahertz? That's what hydrogen creates. 1420.41 megahertz. What could... Oh, you got really close then. So maybe yours is the only trustworthy piece of data in this whole class. We've got one person who did it right. Just kidding. Why do you think we're getting slightly different frequencies? Seems unlikely that it's just human error. Do we have any physicists in the audience? Yes. That's right, student. So students, raise your hand if you've heard of Doppler shift before. It's okay if it's not everyone. See here. So Doppler shift happens when you, when an ambulance is driving by on the highway. You get that high pitch to low pitch as it passes you by, right? So I could take this source, which for us is a hydrogen cloud of hydrogen, and I could have it move relative to an observer, which in this case is us here on Earth. And notice that as it was moving closer, what happened to the wavelength? It compressed, yep. The frequency got higher, yep. And then when I move it away, what does the observer see? Wavelength is longer, frequency is lower. Hey, that's exactly what we're seeing in our data. We're seeing higher and lower frequencies, right? Just a little bit. Still pretty close to that special frequency. So let's make sure we understand. Help me fill in the blanks here. If a signal is getting closer, it is shifted to a what wavelength? Shorter wavelength and a higher frequency. If a signal is moving away, it is shifted to a longer wavelength and a lower frequency. So look at your data and figure out which ones are lower frequency and which ones are higher frequency. Then the special, which one is it? What's the frequency, the special one? 1420.41. 1420.41 megahertz. So just maybe like draw a line where 1420.41 is on your data. And everything to the right is going to be higher frequency, right? And everything to the left is going to be lower frequency. So do you agree with me that we know why we're detecting different frequencies? It's because we're detecting hydrogen clouds that are moving at different relative speeds to Earth. Give me a thumbs up if you agree. These hydrogen clouds are moving at different relative speeds to Earth. That's what's going on. Earth could be moving too. It's a relative speed, right? We could be moving towards them, they could be moving towards us. Either way would create that same shift in frequency. So we've got to keep both possibilities in mind. But now we've got some pretty good data, and we're good scientists here, so let's actually look for patterns. That's what good scientists do, right? Maybe we want to see if the frequencies are consistently higher in some areas, lower in others. Maybe similar parts of the Milky Way show similar data. Are there a consistent number of peaks in certain parts of the sky? So to help us out, we've got a handout where I have reorganized the data according to low frequency to high frequency. And it's still in the order of galactic longitude. So let's go ahead and hand those out. And just be a good scientist. Just look for trends. Talk to each other and just say what you notice. All right. I think there's really good conversations happening if I've never seen people stare at data so deeply. This is wonderful. So did you notice anything? There's some missing data. There's some missing, you mean like these blank spaces? Or this one right here? Oh, yeah, like right here? Yeah. And part of that's just kind of how I divided it when the hour that I sat there tediously doing it, so. Yeah. Does everyone agree that there's a glaringly obvious bifurcation of the data? The middle part seems to clump to the high frequency, and the bottom part really seems to clump to those low frequencies. Do you agree? We're all looking at the same data. So those high frequencies, what did they mean again? The high frequencies are Doppler shifted, and that stuff is what? What's happening with that stuff? Higher frequency means coming closer together, and the low frequency stuff is getting farther, right? Okay, so all the high frequency stuff is galactic longitudes. Oh, that 90 and 270 needs to be moved down. The galactic longitudes are kind of like, what, 60 to 100 or so? Do you agree? And the things that are moving farther, the low frequencies, sort of like 175 to 200. Okay, so there's this whole stuff over here that's getting closer to us, and a bunch of stuff over here that's getting farther from us. But there's those two possibilities, right? That stuff is moving towards or away from us, or we're moving towards or away from it. So what do you think is more likely? Do you think Earth's at the center of this huge galactic motion? and that that whole section of the galaxy is moving towards us, and another whole section of the galaxy is moving away from us? Or do you think Earth is moving, and the Doppler shifts we see are mostly from the motions of Earth, meaning that we are moving towards a certain direction and away from another direction? What do you think is more likely? Are we at the center of things, or we are just detecting ourselves? What do you think? We'll vote. Use 1 for choice 1 or 2 for choice 2. 1, 2. Yeah, choice 2 seems more likely, don't you think? So, if we all agree it's probably our own motion moving through the galaxy, which direction are we moving? Are we moving the green direction clockwise, or the orange direction counterclockwise? We're going to vote. If you want to say clockwise, do the 1, and if you want to say counterclockwise, do a 2. So 1, 2, 3. Awesome. Seeing lots of 1s. That makes sense, doesn't it? Like, we're probably orbiting the galactic center clockwise, because if we're moving to the left, we're going to be getting closer to all that stuff and leaving that stuff in our tracks, right? Leaving it in the dust. So that's really cool. Totally unexpected finding, but sort of undeniable when we look at the data, right? There's just that 2 different distributions, super obvious. That's great. We could write a whole publication about that, and we'd be like a third of the way to our PhD or something. But that's not our question, right? So we still got to get to the question at hand, is what's the shape of the Milky Way, right? So cool, we wrote a publication. We're still trying to answer our burning question. So another thing we could do is look at similar frequencies. So I've just color-coded them here, where the first column, is like 1419 point something, 1420 point zero something, 1420.1 something, 0.2 something, 0.3 something, 0.4 something, 0.5, 6, 7, 8, and 9. So starting to see some trends that way. It seems like some frequencies change consistently across a range of galactic longitudes. Do you agree? Okay, so that seems important. We're seeing consistent signals across a whole range of the sky, whole range of the galaxy. So do you think we're observing random hydrogen clouds or large structures of hydrogen? Raise your hand if you think, or say, do A for random or 2 for large structures. Okay, seems like these structures are these signals are similar, they seem connected. So what are some other large structures we see in other galaxies? Come on. Spiral arms, guys. The large structures are the spiral arms. Each different peak of your data is from a different spiral arm. Hopefully mind blown. Do I know which peak comes from which spiral arm? Not really at this point. I'm guessing that this little one is from the spiral arm that's farthest away. I'm guessing that if it's far away, it probably has a weaker signal. That's just what I think. I don't have proof, right? But along this one line of sight, if I'm detecting 3 peaks, it must be because I'm seeing 3 spiral arms. So this is literally how this modern day map of the Milky Way was made is data like this and more analysis and data taken in other wavelengths as well. But this is no simple task, and this is no closed book. This is our best guess for what the Milky Way looks like because we're still mapping it. This is an artist's conception based on real data as of 2008. So we even have names for the different spiral arms that we believe exist. We've figured out that we think there's a bar structure at the center. But it is through this process that we're figuring that out, primarily radio astronomy. So we may not have proof, but we can say, do our data support this depiction? Where's the music coming from? Oh, that's cool. It just got more exciting. So when we look at longitudes between 0 and 90, so this quadrant, right? We should, according to this map, we should see like multiple peaks, right? Like at least 1, maybe 2, 3, 4, maybe 5 peaks if we look through that line. So is that true? When we look between 0 and 90 degrees, do we get several peaks of data? Okay, okay. What about when we look at longitudes near 180, like those outskirts of the galaxy? Maybe we just see that one spiral arm. So do we see fewer peaks or even only one? Raise your hand if your data only had one peak. Okay. So is it consistent with this map? Yeah, it's consistent. Maybe like the brown-yellow maybe like the brown-yellow signal here that stretches like the whole length of the galaxy, maybe that's like this Perseus arm that stretches like this whole length right here, because we see it throughout. Maybe like the green and blue is sort of that next arm out Sagittarius arm, or the sort of just the inner part, because we don't see it in the outskirts of the galaxy. And then that sort of most distant, the most Doppler shifted orange frequencies, I mean, they're the most Doppler shifted, so they're the ones that are moving most differently from us. So maybe they're the ones from the most distant spiral arm. I don't know. Like, what do you think? What do you think? I don't know. I'm looking at the same data as you. I don't have any additional information at this point. This is not my area of research. So, yeah, maybe we need more and other types of data, but I'm pretty convinced by this data that we live in a spiral galaxy. What about you? What do you think? You think we live in a spiral galaxy? Cool, case closed. So now when someone asks you what's the shape of our galaxy, you could say spiral galaxy. And when they ask you, how do you know? You can say, I've analyzed the data myself. And with this same data, and I'm not going to go into it today, I'm going to maybe spare you or tempt you. You have the data, you can calculate this yourself. With this same data, we can also show that our galaxy is spinning so fast. Remember, Doppler shift gives us information about motion. So we could actually calculate how fast is that motion? How fast are things really moving? And whoa, they're moving fast. Way too fast for our galaxy as far as we can tell by stars. Meaning that there must be more gravity than we're aware of, because our galaxy should be flying apart. It's spinning so fast. It should be ripping itself to shreds. But there must be more gravity holding it together, holding it intact. And gravity comes from mass, so there must be more mass than we're aware of. There must be more matter that we don't see. So this data implies the existence of dark matter as well. And I haven't gone into those calculations, but for the interested student, front row physicist here, you can easily do it. And it's a lab that we do with freshmen. So it's not that hard. It just takes a little bit of trigonometry. What is trigonometry? SOHCAHTOA, that's what it is. That's all it is. So, like I said, I'm not a radio astronomer. My dissertation was on students' understanding of gravity. So I'm an educator, a physics and astronomy educator. But I learned this project when I was working at the Green Bank Observatory. And we would do this with middle school kids. And they would do it on, like, with an actual telescope. They'd be moving the knobs and recording it on a chart recorder paper. They wouldn't need the internet like we are using right now. And so when I came to WVU, I was like, we've got to do this in the intro astronomy class because every person can take their own data and we can work together collectively, and it's not that hard. So I asked students before and after this project, when I first introduced it, and I said, we're going to map the Milky Way. Do you feel like a scientist? And then we did map the Milky Way. Do you feel like a scientist? And students felt significantly, like statistically significantly, more like scientists after this. And we really spread it out. It's about a month-long process in my astronomy class at WVU. And we really dig in. And these are some quotes from my students. Feel more like a scientist than ever. That's like my dream come true, right? Like a scientist in a team of scientists. Like an amateur scientist. I needed so much guidance. Yeah, some students say, I don't think I could have done it alone. I learned a lot about the nature of science, just how science even works. And some people don't feel more like a scientist. They say the most crucial part of science is discovering things that have never been discovered before, which is a valid view, valid point of view. Let's do a poll. Do you feel more like a scientist? Raise your hand. Cool. And of course, there's more to life than being a scientist. Sometimes you want to have fun. So some students felt like this is fun, this is interesting, that it's cool because anyone can do it. You can get online. And in my class, I have a lot of future teachers, so that's a really big deal that one of the future teachers in my class said that her views on teaching have changed as a result of this. That she realizes how important it is to boost, establish a science identity and empower people to learn for themselves. Students say that I've become inspired, and it literally blows their mind. So, like I said, I couldn't do this alone. I've got tremendous thanks to Sue Ann Heatherly, my former boss at the Green Bank Observatory, Dan Reichert and the UNC Chapel Hill Skynet team. They're the ones who run the Skynet online interface. European Union Hands-on Universe has a lot of good online resources for this. WVU has been extremely supportive of me pursuing this because Skynet time is not free, we pay for it. And thanks for bringing me here, Kevin. This is the first time I'm ever doing this, but I am very, very passionate about climate change. And here I am on a platform as a scientist. I have to say, as a scientist, climate change is happening, it's human caused, and we need to act now. So, thank you very much for having me here. Can I answer any questions? Yeah.
So, I knew that I wanted to be a physicist when I was 8.
Wow.
I am a physicist.
And you're the only one that got 1420.40. Yeah, so.
I did not feel like a scientist until I was 29. So what does it mean for a student who comes in and does your exercise, and I think your exercises are great, to say they feel like a scientist? What does that mean? I don't know what it means.
I think it's open to interpretation. It's a philosophical discussion, isn't it? What is a scientist? I've talked to a lot of teachers about what science is and how science works. And a lot of the teachers I've talked to said that you're a scientist when you're born. A human is a scientist because you're analyzing data all around you all the time, whether you realize it or not. It's how you learn things from day one. So that's the definition of scientist that speaks to me. It's using data around you to learn and make decisions, and every human can do that. But some people feel like you need to be a professional with funding and publications.
Well, that's necessary, but it's not sufficient.
Other questions? Oh.
I was just interested when you talk about visualizing dissipation. Do you students understand gravity?
You could probably guess the most common misconception. There's no gravity in space, right? Why would astronauts be weightless if there was no gravity, if there were gravity in space? That's the biggest misconception, right? Because you see these astronauts floating around apparently weightless. So untangling that force of gravity from apparent weight is pretty difficult, actually. And honestly, it's very deep thinking, and that's what inspired Einstein to reconceptualize gravity. So it's not surprising students get confused by that. They're not dumb, right? So that's the biggest one. Another misconception is that gravity has like finite length scales or mass scales that it works over. Like gravity only works when you're really close to something, right? Rather than that sort of 1/r² drop. Or you have to be really massive to exert gravity on something else. That's why astronauts wore heavy boots on the moon. That's one of the big ones. So those are some of the ways that students misunderstand gravity. Thanks for asking. Yeah?
Did the data query you submitted earlier come back?
That's a good question. Let's look. Let's see what data was collected from the Milky Way today during this lecture. Here it is. Look, it says completed. Gonna click on it. Oh my gosh, 2 spiral arms. And we can see what the location was. It's around, 298. Can that be true? 298 galactic longitude. Maybe we can see that longitude. That one's a little surprising to me. I'm like doubting myself a little bit. But, and then you can see one of the channels was broken on the telescope, because a radio telescope, you have 2 little antennas, and so you get twice the data for the price of one, but one of them is broken right now. So I can also like zoom in and actually measure it, which is what my students did. They were not dealing with printouts like you have right now. They actually could manipulate this online and zoom in and hover. And you see when I hover, it gives me a reading down here. 1420.26 is the frequency of that peak. So my students' data is probably more accurate than yours. But this is our data that we collected, you guys, just now. It's pretty cool. We're totally scientists. Thanks for asking. I totally forgot about that. Anything else? Yeah. Hi.
I have family members that still think that climate change isn't real. How can I scientifically explain to them and elaborate that this isn't real?
I wish I could solve that, right? There's a whole body of literature on how to communicate science, or the climate change science. And it unfortunately shows that data isn't very convincing to the average person. So showing them a bunch of charts and graphs and numbers is probably the worst way to do it. Kathryn Hayhoe, who I was quoting on that last slide, she gives a TED Talk this is the name of the TED Talk. The most important thing you can do to fight climate change is to talk about it. So I think you just got to start talking about it and find some common ground. And she has even talked about how she goes to fossil fuel industries and she genuinely seeks to find common ground with them. And one of the things she found is she is genuinely thankful for the modern world we have that has been brought to us by fossil fuels. So if you can find anything that you can truly, genuinely connect on, that's probably the best starting point. Good question. Yeah. Anything else? Well, thank you guys. I've so enjoyed this. Thank you so much.